So if we look at an example, we consider a mixture of air and gasoline in a cylinder. We have an initial volume of 40 cubic centimeters. We explode the mixture, releases 950 joules of work of energy. If we are expanding that against a constant pressure of 650 torr, and we're allowing the expansion to go whatever volume is necessary, we are saying that all the energy combustion is converted to work to push back the piston. So the combustion is putting 950 joules of energy in there, and all of this energy is going into work. So the energy is going into the system in terms of heat of combustion, but it's all leaving the system through work. So our internal energy ends up being zero. So we're only looking at pressure volume work. So we put that in for our W. We get Q minus P delta V equals 0. So we rearrange the equation and solve for our delta V, and that will give us heat divided by pressure. So our heat is the 950 joules. Our pressure is 650 torr. Well, our first step is to convert our torr into atmospheres, so we divide our 650 torr by 760 torr. That'll give us atmospheres. We are looking for volume. So what is good to do then is convert our joules into liter atmospheres. So that way we can get liters out of this system. So we take our joules, we divide it by the 101.3 joules in a liter atmosphere. That will give us liter atmospheres. We're taking liter atmospheres, dividing it by atmospheres, which will give us liters as an answer. We do the calculation, we see that our increase in volume is 11 liters. That's our increase in volume. We said the original volume was 40 cubic centimeters, which is 0.04 liters. Two significant digits though. We have 11.0 liters. The initial volume is smaller than the significant digits on 11.0 liters, so our final volume is 11.0 liters. So when we do reactions in terms of pressure volume work is going to be based on the change of volume of gas in the reaction. If we create a gas, this gas will have to push the air away from around it. That's doing work in the surroundings. So if we're allowed to expand volume at all, which we do when we're at constant pressure, any gases that we make is going to do work in the surroundings by pushing air away. So to see if we're doing work, we just see how many moles of gas are present on both sides of the reaction. On this first reaction, we have no gas on the left, we have 1 mole of gas on the right. We are creating 1 mole of gas, we are increasing the moles of gas. This reaction is doing work in the surroundings. Second equation here, we have 1 mole of reactant gas, we have 2 moles of product gas, so we have increased the moles by 1. We are doing work in the surroundings. If we lose gas pressure, gas is removed from the system, then air will rush in to fill that space. So the air is doing work onto the system, so the surroundings is doing work on the systems when we remove gas from a system. So in this reaction here we have 3.5 moles of gas for the reactants and no moles of gas for the product. So we have lost 3.5 moles of gas. So the system has been worked on by the surroundings. The surroundings has worked on the system. On this bottom one, we have 1 mole of gas on the left, 1 mole of gas on the right. We have no changes in moles of gas. This reaction does no work, and no work is done on this reaction. Enthalpy. Enthalpy is heat flow. To make our life simpler, make the math simpler, if we work at a constant pressure, we get a particular type of heat flow that we call enthalpy. A constant pressure heat flow is called enthalpy. Enthalpy is heat flow at constant pressure. So, this equation down here, enthalpy plus internal energy plus work, now where does this come from? We have internal energy is equal to heat plus work. Work would be a negative PV. Q would be H, enthalpy. So we would end up with energy is equal to enthalpy minus PV. We rearrange the equation and get enthalpy is internal energy plus PV. So the enthalpy reaction is related to internal energy by the difference of the work of the system. Now, of course, we don't get the absolute values of these. We always work with the change in values of these. So the difference between the enthalpy and the internal energy exchange in a process is related to the negative of the work. So if the system is doing work, it's expanding, our P delta V here will be positive, and our enthalpy change here will be more positive than the internal energy change. That is when we are doing a work process, it's doing the work. If work is being done on this, then the enthalpy will be more negative than the delta E. So enthalpy change, we always do final minus initial for change. Final will be products, initial will be our reactants. So our enthalpy change is the enthalpy of the products minus the enthalpy of the reactants. Enthalpy is a state process, so we just have to identify the products and reactants. It does not matter the process to go from one to the other. If we have an exothermic process, our delta H is going to be negative. If we have an endothermic process, our delta H is going to be positive. Enthalpy is an extensive property. It depends upon how much material is present. So if we double the amount of materials reacting, we're going to double the enthalpy. If we reverse a reaction, we are changing the sign of the reaction. If we reverse an exothermic reaction, we create an endothermic reaction. If we reverse an endothermic reaction, we create an exothermic reaction. And the enthalpy of the reaction will depend upon the physical states of the reactants and products. So if we have water participating in the reaction, the enthalpy will depend upon whether we have liquid water gaseous water or even solid water. For our reactions, we're going to write out our reaction, and then we're going to give a enthalpy associated with that. And the enthalpy will just be given in joules or kilojoules, normally kilojoules, and it won't have a per mole associated with this. That is because that enthalpy is for the reaction as written, which means it's per 4 moles of copper 2 oxide is per 2 moles of copper 1 oxide, and it's per 1 mole of oxygen. So to include that into our calculations, we're going to take our enthalpy of reaction, divide it by the coefficient of the compound that we're interested in. So enthalpy divided by coefficient will give us our kilojoules per mole, and then we multiply that by how many moles of the compound we have present, and that will give us the heat of that reaction for the amount of compound present. So in this case we have 5 grams of the copper 1 oxide. We're going to convert our 5 grams into moles of copper 1 oxide, and we're going to divide our 288 kilojoules by the 2 moles of copper 1 oxide. So we take our 5 grams, divide by molar mass to get moles of copper 1 oxide. We're going to take our 288 kilojoules, divide by 2, and then multiply by the moles of copper 1 oxide, and that will give us 5.0 kilojoules for that reaction with only 5.0 grams of copper 1 oxide being produced. We give some types of enthalpy specific or particular names. This will mean different subscripts on them. Heat of formation. Heat of formation is the enthalpy of forming a compound from its elements in their standard states. So standard states would be the most stable state at 25 degrees Celsius and 1 atmosphere of pressure. So 298 Kelvin, 1 atmosphere of pressure. The elements in their most stable condition at those states are their standard states. So the heat of formation of silver sulfide. Silver sulfide is a solid at 25 Celsius, 1 atmosphere pressure. So we're going to be forming it from silver and sulfur. Silver is a solid at 25 Celsius and 1 atmosphere. And sulfur also is a solid at 25 Celsius, 1 atmosphere. So the process of taking solid silver, reacting with solid sulfur to form our solid silver sulfide, that heat of enthalpy is called enthalpy of formation. One of our common ones that we love is the heat of melting a solid is called the heat of fusion. So fusion here represents melting, does not represent the nuclear reaction that occurs in the sun. It just represents melting. It also represents freezing, the reverse process. So to go between a solid and a liquid, that enthalpy is called enthalpy of fusion, heat of fusion. So delta H subscript FUS for fusion. To go from a liquid to a gas is called vaporization. The heat of that process is called the heat of vaporization or enthalpy of vaporization. Delta H with the subscript VAP for vaporization. This will also work for condensation, going from a gas to a liquid, with a change of sign, of course. But to go from a liquid to a gas for any compound is the heat of vaporization. We know that the heat of fusion and the heat of vaporization are endothermic processes that are going to be positive processes. They would be exothermic for the reverse process, for freezing and for condensation, a negative delta H. But for melting and vaporization, they are endothermic with a positive delta H. Heat of formation can be positive or negative, a wide range of values for heats of formation. Last one here is our favorite, heat of combustion. We use this to drive our cars, heat our houses, cook our food. So when we combust a substance, combust is a rapid oxidation with oxygen gas. Usually we're burning or combusting a hydrocarbon. So when we burn things, the heat that is given off from that process is an exothermic process, is called the heat of combustion, delta H with a subscript COMB for combustion. So it's a rapid process giving off heat and light because it's exothermic. If it was not exothermic, it would not burn. So burning, this rapid oxidation with heat and light, is combustion, and combustion is exothermic.